Okay, so my game plan for today, I'm actually finished with everything for this coming test, but I'm going to start lecturing from 4.1. Since I'm ahead, I might as well stay ahead. Okay, so I'll lecture a while. A while probably means I'm not going to do any problems unless you want me to. Okay, and then I'll let you ask questions for the test for the rest of the hour. And same thing for tomorrow. Tomorrow, I'm prepared to let you have the entire class period for a Q&A session, question and answers. But if you don't have anything, I'll keep going with chapter 4. Today, you don't get a choice. I'm going to start lecturing on 4.1. Okay, but since I'm 2 days ahead, I might as well stay a little bit ahead. Okay, so again, I've already finished everything I need to cover for this Friday's test, but just to stay ahead, since I'm already ahead, I might as well start doing some of 4.1. But anything I do today or tomorrow won't be on, this test. It'll be on the next test, whenever that is. That isn't going to be until what looks like November the 13th, something like that. All right. So I'll begin lecturing some of 4.1, and then after I've quote unquote lectured enough, then I'll stop and ask you if you have any questions that you want to go over for chapter 3. But if you don't have anything, I'm just going to keep going with chapter 4. And same thing for tomorrow. Tomorrow, I'm prepared to let you have the entire day. Why is this thing blinking? Okay, I'm prepared to let you have the whole day, but again, if you don't ask questions, I'll just keep going with chapter 4 stuff, okay? All right, so even while I start lecturing now, if you want to start putting stuff within the chat, you may, or if Prasanna's there, Prasanna can maybe answer some questions for you. All right, so I'll get started with sum of 4.1. You can take notes casually or not at all, since none of this will be covered on this coming test, but will be over here. Okay. And by the way, chapter 4, as you can see, isn't as big, and the last one isn't as big. So chapter 3 was definitely the biggest, right? Chapter 1 was not very big at all, but chapter 3 is our biggest, and then chapter 4 not as much. And notice we're not even doing all of chapter 4. It looks like we're skipping 4.6. Okay. And again, 4.9 I'm lumping together with chapter 5 for some reason. Okay. So chapter 4 is applications of differentiation. So starting on page 276. I'll get you started with some vocabulary, some theorems, and then after a while I'll stop and let you ask stuff. Okay, maximum and minimum values. We've touched on that subject already a little bit. Okay, so they give us graphs here, for instance. So again, on page 276, absolute maximum, absolute minimum. Okay, now they give you a very formal definition of absolute maximum, absolute minimum. Okay, it's true, it's correct, but I don't think you really need it. The absolute maximum of a graph is absolutely the highest point. Okay, so let's take this particular graph. That looks like the absolute maximum. It's absolutely the highest point. That looks like an absolute minimum. Okay, by the way, these things don't have to exist. Okay, some graphs don't have any absolute maximum or absolute minimum. Okay, let's see, figure 1, that point looks like the absolute maximum. That looks like an absolute minimum. Right? No big deal. Okay, absolute maximum, absolute minimum. It's absolutely the highest point or lowest point. Okay. We could have local maximum or minimum, or sometimes relative. You'll hear me use both expressions. I will sometimes say relative maximum or minimum, or local maximum or minimum. Again, this is a very formal definition, but within a small neighborhood of the point. If I just go close by, relatively speaking, it's a maximum or minimum. So you see local, they put LOC. I might put REL for relative. Okay, so this is a local maximum because in a small neighborhood, that's indicated by the shaded region. Okay, in a small neighborhood, it's the highest. Now, there may be some other points higher in the graph, like over here. So it's not the absolute maximum, but locally or relatively speaking, it's a maximum. Likewise, local minimum within a small neighborhood, the small shaded neighborhood, is the lowest point. Now, if I look at the whole graph, there are points that are lower, but in a small neighborhood, this is the lowest point. Okay, what this is saying is local and absolute minimum. So it's absolute minimum, therefore it's also a local minimum. Okay, if you're at an absolute minimum, then of course you're at a local minimum. And likewise for maximum, this is an absolute maximum, so automatically it's a local maximum. Okay, I guess think of it, yeah, you might have a local maximum within a small region, small neighborhood, it might be the highest, but not for the entire graph. Okay, by analogy, it's a think worldwide. So if you're absolutely the best at something, okay, so you won the Olympics, right? And you ran a race and you won the Olympics, so you're considered the fastest in the world. Okay, so if you're the fastest in the world, therefore you're automatically the fastest in your neighborhood. Okay, but not the other way around. You might be the fastest on your block or the fastest in your neighborhood, but that doesn't mean you're the fastest in the world, right? So to speak. Okay, so that's the idea behind local and absolute. And for absolute, sometimes it's called global for that reason, global, worldwide. Okay, so this is a global or absolute maximum, right? It's absolutely the highest, right? So therefore, it's also locally the highest. Okay. On the other hand, let's say this one here might be a local maximum. Locally, it's the highest, but it's not worldwide, so to speak. It's not absolutely the highest. Okay. So this is locally a maximum. This is like the highest point on the block, but you're not the highest in the whole world, so to speak, right? So there are other points that are higher. Okay. So local maximum, local minimum. I might say relative. REL is my abbreviation for relative. Okay. And you'll sometimes hear absolute as global, although I won't say it that much. Okay. All right, so on this page, y equals x squared. We know we have a minimum. The minimum value is 0. Happens at the origin. So 0, 0 is a local minimum. It's also the absolute minimum. And of course, there's no maximum because this just goes up, 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 up on both sides. So this one we would say no maximum, a local minimum and an absolute minimum at the origin, 0, 0. So the minimum value is 0. Okay. Here's y equals x cubed. No minimum, no maximum. Right. So these maximum and minimum points don't have to exist. Right. This graph we know just goes up, 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 and down, 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 down. So there's no maximum, no minimum. Okay. This looks like a trig function, cosine. Right. So you have local and absolute maximum values. In fact, we have a tie for a whole bunch. Right. There's a whole bunch of absolute maximum values at 1. Right. We know it's periodic. So there's another one here, and there's another one here, and another one here. Right. And we have local and absolute minimum values at y equals -1, at pi, 3 pi, 5 pi, and negative pi, right? So you could have ties, of course. That's certainly allowed. Okay, and they give you some graph on a closed interval here. So from -1 to 4, they graph this function. You will be graphing some of these. Back in this section, we will. Okay, so it happens to look like this. All right, so they ask for local max and absolute max and so on. So this is what the graph looks like. This looks like an absolute max, right? That looks like a local max. Okay, locally it's the highest. That looks like a local min. That looks like a local min and also the absolute minimum. Okay, so if I just take a small neighborhood at this point, it's the lowest. But if I look at the whole graph, globally, worldwide, it is the lowest. And how about that? That looks like a relative maximum, right? So I'll say relative or local. So if I just take a small neighborhood at this point, it's the highest. But there are points that are higher on the graph. Okay, so absolute max, absolute min. Local max, local min. And I would still say this is a local max also. And this is a local or relative min. Okay, so again, if you're worldwide, you're also local, right? But not the other way around. This is absolutely the lowest point, so therefore relatively so speaking. Okay, so if you're the fastest runner in the world, you're also the fastest in your block. right? But not the other way around. Right? You might be the fastest locally on your block, but that doesn't mean you're the fastest in the world, right? Because that's sort of the concept here. Okay. Now you might notice something right here. What seems to be the slope of the tangent line? Looks like it's 0. And what's the slope of this tangent line? 0. And what's the slope of this tangent line? 0, right? So it looks like if I have a maximum or minimum point, okay, the derivative is 0. You say, well, what about here? Okay, well, these might be max or min just because they're endpoints, right? This turns out to be absolutely the maximum point, right? The slope here isn't 0. Looks like it's going like that. Yeah, that's because it was cut off. I mean, the way the graph is going, right? If I didn't have this restriction, it looks like it would just keep going higher. So this would not be a maximum or minimum. Likewise over here. Okay? So you might have a maximum or minimum at an endpoint just because the graph got cut off. Okay? In between, though, it looks like slope is 0, right? Slope is 0, slope is 0. Now, slope is not 0 here. That's because the graph got cut off. Likewise, slope is not 0 here. It got cut off. Okay. Page 278, extreme value theorem. What is the extreme value theorem? Okay. That actually applied to that previous picture. Okay. We have a continuous function on a closed interval. This is a closed interval. It's a continuous function. We have to have an absolute max and min. That's what the extreme value theorem says. If f is continuous on a closed interval from a to b, notice it's bracket. Bracket A, B, bracket on both ends, then f attains an absolute maximum value and an absolute minimum value. Okay, so here's a picture. Closed interval, continuous, there's a maximum and a minimum. So the way they have it, that looks like a max, that looks like a min. Here's another picture, right? So there has to be a max and a min. That looks like the maximum, that looks like the minimum. It might be at an endpoint. Okay, here's a continuous on a closed interval. So it looks like we have a tie for the maximum. You can have ties, but that looks like the maximum and it looks like a minimum. Okay, now figure 9 and 10, they're trying to show you if you don't have a continuous function, you don't necessarily have to have a maximum or minimum. So here's a function which is not continuous. So there actually is no maximum value. There's an open circle at 3. Okay, so we actually don't have a function value, right at 3. It looks like we have 2.9 and 2.99 and 2.999, but not quite 3. So there is no maximum value. Okay? And as you can see, that's not violated by the extreme value theorem because you have to have a continuous function. This is not continuous. Okay, then figure 10 says it has to be continuous on a closed interval. If you have an open interval, then this thing can shoot up to infinity, right? So notice this shoots up to infinity. So we do not have any absolute maximum. That's because we're not in a closed interval. We're in an open interval. We're not counting 2. Looks like we're not counting 0 either. So this has no minimum either, looks like. All right, and then this picture here, figure 11, just like what we said, right? That looks like a maximum, right? That looks like a minimum, locally or relative. Relative minimum, relative maximum. There might be some points that are higher. There might be some points that are lower. But relatively speaking, highest point. But just take a small neighborhood, right? It's the highest, lowest. So what are they trying to show you in red? Slope is 0. Slope is 0, provided the derivative exists. Okay. So we have something called Fermat's theorem on 279. Again, I'd say don't even take notes now because you're focusing on the test on Friday. But Fermat's theorem, if f has a local maximum or minimum at c, if the derivative exists, then it's equal to 0. Very logical. Okay. And that's borne out from this picture right here, right? Maximum, minimum. Derivative exists, it's 0. Derivative exists, it's 0. Now look back over here. Maximum, minimum. Slope is 0, slope is 0, slope is 0. Slope is 0, slope is 0, slope is 0. Okay? Again, that's if the derivative exists. You could have a maximum or minimum where the derivative does not exist. Okay? So on page 280, show you this. Y equals absolute value of x, right? That's a minimum point, but the derivative does not even exist here, right? It's a corner point. Okay, so that's why the theorem said if the derivative exists, if f prime exists, then the derivative is 0. Here's a case where the derivative does not exist, but you still have a minimum. That's okay. Okay. What about this? Y equals x cubed. They're trying to show you here that the converse of Fermat's theorem is not true. Okay. You say, what do you mean by that? Okay. If you have a local max or min and the derivative exists, it's equal to 0. But the converse means if you switch it around, if the derivative is 0, do you have to have a local max or min? The answer is no. And here's a typical situation. Y equals x cubed looks like this. Okay. The slope at the origin is 0. By the way, you can prove that easily. Y equals x cubed. What's the derivative of x cubed? 3x squared. So what do you get when you plug in 0? 0. So the slope at the origin is 0, but you can see you don't have either a maximum or a minimum. Okay. So that Fermat's theorem on the other page, it's one way. Okay. If you have a max or min and a derivative exists, it's 0. But if you have a derivative of 0, that does not guarantee that you have a maximum or minimum. You might have a max or min, but it's not a guarantee. Okay, so over here, the derivative is undefined. Okay, so we have, this is more vocabulary. Okay, a critical number. Okay, again, for now, don't worry about it. I'm just giving you a heads up, or a head start, I should say, for next week. A critical number of a function is a number in the domain of f such that f prime of c is either 0 or f prime of c does not exist. Okay, so critical number means derivative is 0 or derivative does not exist, but the function exists. Okay, what's so good about having a critical number is it'll enable us to get maximum or minimum values like this. Okay, so a major part of the next chapter of all this stuff, a major portion is finding maximum and minimum values, maxima or minima. So the way we would do it is to take a derivative, set it equal to 0, and also find out where the function, the derivative is not defined. Okay. So that gives us D. If f has a local max or min, then at C, then C is a critical number. Okay. So critical numbers, we will test for the derivative either being 0 or the derivative is undefined, and that gives us a test for possible max or min. Okay. All right, then there's something called the closed interval method. I won't talk about it until next week, unless you want me to, and the questions stop from here on out. Okay, so there's some problems later on that does something about the closed interval method. How do you find absolute maximum? So by the extreme value theorem, we already talked about that. The extreme value theorem, the maximum and minimum exist. So this gives you a technique for finding the absolute maximum and minimum on a closed interval. Okay, you're basically going to set the derivative equal to 0 and find critical numbers, and then you also check the endpoints. Okay, but we'll worry about that later. Okay, so that's just an introduction. I know I've spent almost half the class period, but at least that means I don't have to go over that next Monday, right? And then next Monday, I'll just quickly run through this, then I can get started with some of the homework problems. Okay, but the rest of today, I'll go ahead and take stuff from you to review for the test, assuming you have that. Okay, so let me stop the share and check the chat because I can't do both at the same time. Let me check the chat. Okay, so let me see. I guess I'll just go in order for now. 3.5, 21, 25, 54, 3.2, 19, 47, 3.4. Okay, so it looks like I'm not going to get through all of these for sure. And again, to make it better for everybody, I really don't want to do a problem that wasn't assigned. Okay, so if you ask me for a question that wasn't on the original assignment list, I am very likely not to want to do it unless, you know, we have time. 3.3, 31, 3.9, 15. And yeah, if I just recently did a problem, I may not be willing to do it again. Somebody mentioned 3.1, 61, 3.95, 3.97. Okay, so let me double check that I wrote this correctly. .1. Okay, so I think I've got everything up there now for the check. Okay, you can still keep typing, but to be honest with you, I'm pretty sure I'm not going to get through all of these, but we have all of tomorrow. So yeah, again, tomorrow I'll let you have right from the get-go, right at 12:10. You can ask questions the entire period, but if that stops, I'll just go on with more chapter 4 stuff, okay? So let me go back to sharing the screen. Okay, so let me see. Yeah, 3.161, I did go over that, so please look at the notes from yesterday. So I don't want to do that one. 3.219, let's see. And 219. Yeah, this is one of those where you don't want to do the quotient rule. You don't have to. I would just do s divided by s squared, and then radical s over s squared, and then I can avoid that. Okay. Now keep in mind that's s to the 1/2. So s divided by s squared is s to the -1. S to the 1/2 minus 2 is s to the -3/2. And that way I don't have to do the quotient rule. In fact, this section was before the quotient rule anyway. Okay, so dy ds is negative s to the -2. -3/2 times -1 is plus 3/2 s to the -5/2. And the original problem did not have any negative exponents, so -1 over s squared plus 3 over 2s to the 5/2. Okay, so that's about it for that one. Okay, so that's 3.219, 47, 3.247. What do they say? G of x is x times f of x. F of 3 equals 4, f prime of 3 equals 2. Find the equation of the tangent length of the graph at the point where x equals 3. Okay, so let's find f of 3. Or rather, sorry, g of 3. G of 3. G of 3 is 3 times f of 3. F of 3 is 4. 3 times 4, which is 12. Okay, so the ordered pair is 3, 12. Now I need the slope. So g prime of x, product rule, first times derivative of the second, f prime of x, plus second times derivative of first, which is 1, Then I plug in, what do they want? 3. G prime of 3 is 3 times f prime of 3 plus f of 3. And what is f prime of 3? 2. And plus f of 3 is 4. So 6 plus 4, 10. Point slope. Y minus y1 equals m times x minus x1. Okay. All right, 3.331. F of x is equal to tangent x minus 1 over secant x. Use the quotient root first. Okay, so bottom times the derivative of the top, derivative of tangent is secant squared, minus the top, times the derivative of the bottom, derivative of secant x is secant x tangent x, all over the square of the denominator. And then there's a lot of cleanup. Secant cubed x minus, okay, let me distribute. So that would be secant x tangent squared x. Right? And then minus a minus 1 is plus 1. So plus secant x tangent x. Okay, so I have this thing now, but I'm going to try to clean it up. Okay, that divided by that is a secant. That divided by that is a minus tangent squared. This one's going to leave me with a secant on the bottom if I cancel. Okay, so I'm going to write secant x minus tangent x plus tangent x over secant x. Okay, I'm going to write that above now. So secant x minus tangent x plus tangent x over secant x. Okay, let me change everything to sines and cosines. Secant is 1 over cosine. Tangent is sine over cosine. Let's see. Secant on the bottom means cosine on top. Whoops. And tangent is sine over cosine. These guys cancel out. So it looks like I have 1 minus sine x over cosine x plus sine x. Okay. And then part B, they want you to simplify first. Okay, so simplify first. Sine x over cosine x minus 1 divided by 1 over cosine x multiplied by cosine x over cosine x. And that gives me sine x minus cosine x. Okay, so they want you to differentiate this. And supposedly that's the same as this. Looks like I may have made a mistake somewhere because I don't see that offhand. But that's the basic idea. So I'll just say etc. And you can finish the rest of that, but that's as much of that as I wanted to do. Okay, so that's 3.3, 3.4. 3.429. H of t, r squared minus 1 cubed, 2r plus 1 to the 5th power. All right, so that looks like a quotient rule. So bottom times the derivative of the top, which is a chain rule, r squared minus 1 squared, times the derivative of the inside, which is 2r, minus the numerator, times the derivative of the denominator, so 5, 2r plus 1 to the 4th, times the derivative of the inside, which is 2, all over the square of the denominator. So if I have something to the 5th power and I square it, that's going to be the 10th power. So 2r plus 1 to the 10th. Okay, and yeah, I would say stop there. The back of the book may not look like this, but they went ahead and did a lot more algebra, but I don't feel like doing that, and I don't think you do either. So what would I expect in an exam? Maybe just 3 times 2r is 6r, 2 times 5 is 10, and maybe that's about it. Okay, so that's as much as I'll do for that one. 35. Y equals cosine of this messy thing, 1 minus e to the 2x, 1 plus e to the 2x. Okay, so you're taking cosine of something, so the derivative is negative sine of that. And then by the chain rule, it's times the derivative of the inside, which is a quotient. Okay, so bottom times the derivative of the top. Derivative of 1 is 0. Derivative of negative e to the 2x is negative e to the 2x times 2, like that, minus the numerator, times the derivative of the denominator, e to the 2x times 2, all over 1 plus e to the 2x quantity squared. And this one, I might actually have you multiply it out. It's not that bad, but to save time, I won't do it. And maybe something cancels out also when you do it. So distribute 1 times that, e to 2x times that, and same thing over here. Okay, so etc. for that one in order to save time. Okay, let's see, 3.5. 3.521, I think we already did, so I don't feel like doing that again. Check your notes for that. 25. Not sure if we did 25. I think we may have. Let me see if I go back and do another. Let me do 54 first. .554 is find a derivative of something. So y is equal to inverse tangent x minus radical 1 plus x squared. Okay, inverse tangent goes 1 over 1 plus this thing squared, that whole thing squared. And then by the chain rule times the derivative of this, which is 1 minus 1/2 1 plus x squared to the negative 1/2 times 2x. And yeah, there's a lot of stuff that might cancel out. That would cancel with that. But to save time, I would just stop there again. Okay. You might be able to get a lot more cancellation, but I don't think it's worth it. So that's what I wanted to say about that one. Okay, let's see. Do I want to go back and do 25? Yeah, I think I can go ahead and do that. So I still have all of tomorrow. What time is it? 10 minutes left, roughly. Okay, 25y sine 2x equals x cosine of 2y pi over 2 pi over 4. Find the equation of the tangent line. Okay, product rule, product rule. First times derivative of the second, derivative sine of 2x is cosine 2x times 2 plus the second function times the derivative of y dy dx. Right hand side, product rule, first times the derivative of the second, derivative of cosine 2y, negative sine 2y times 2 dy dx, plus second function, cosine 2y, times the derivative of the first, the derivative of x is just 1. So there we go. Okay. And yeah, at this stage of the game, it's probably easy to start plugging in rather than trying to solve for dy dx. So every y gets a pi over 4. Pi over 4, pi over 4, pi over 4. Every x gets a pi over 2. Pi over 2, pi over 2, pi over 2. And that's about it. Okay. This is cosine of pi over 2 is 0. Nice, so that's all gone. Sine of pi over, oh, sorry. Let me see if I did that right. Cosine, oh, I'm sorry. I'm taking a cosine of pi. That doesn't cancel out. Sorry, I forgot to multiply by 2. Cosine of pi is negative 1. Right, so sorry, this is pi over 4 times negative 1. So if I plug in pi over 2, I'm taking the sine of pi, which is 0. So that's okay. So that's nothing. Okay, this is pi over 2 times, if I plug in pi over 4, I'm taking the sine of pi over 2, which is 1, times negative 1 times 2, so times negative 2, dy dx. And here, multiply by 2, cosine of pi over 2 is 0. Okay, so negative pi over 4 equals negative pi times dy dx, multiplied by negative 1 over pi, negative 1 over pi, cancel, 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 cancel. I get dy dx is 1/4, unless I made a mistake. So y minus y1, y minus pi over 4 equals 1/4 times x minus pi over 2. Okay, so that was 3.5, yeah, 3.9. 3.9, number 5. A cylindrical tank with a radius 5 meters is being filled with water rate of 3. How fast does the height of the water increase? Okay, I think I already did that, but it should not be too fast, well, it shouldn't be too long. We set you up with that quickly. Radius is 5. So volume, formula is pi r squared h. R is 5. plug in 5, so volume is 25 pi h. dV dt is 25 pi dh dt. They tell us dV dt is 3, so plug in 3 and then solve for dH dt. Okay, so that's essentially it. So just divide both sides by 25 pi. It's going to be 3 over 25 pi. Okay, so that's that. 3.9 number 7 was also asked for. Let's see, 3.9 number 7. The radius of a spherical ball is increasing at a rate of 2 centimeters per minute. At what rate is the surface area increasing when the radius is 8 centimeters? Okay. So setup. So the formula for the surface area is 4 pi r squared. dA dt is equal to 8 pi r dr dt. Then I think you just plug in. Radius is 8. Put 8 there. dr dt is 2. Plug it in. 8 times pi times 8 times 2, which is 128 pi. And this is rate of change of area. So area in this problem is centimeters squared per minute. Okay. And let's see, 3.915. I don't think we had to do that one. Yeah, 3.915 was not assigned, so I don't want to do that one. 3.107. 10 number 7. Verify the given linear approximation at a equals 0. ln of 1 plus x is approximately x at a equals 0. Okay, this is the back of the book, essentially. Right, the back of the book is x. So it's like problem 1, 3, and 5. Okay, where in this case, you don't have to look at the back of the book, that's all. Okay, so a is 0. That a is a particular value of x. So plug in 0, natural log of 1 is 0, so I'm at the origin. Okay, the derivative is 1 over 1 plus x times the derivative of 1 plus x, which is just 1. Okay, and then I just plug in 0. F prime of 0 is 1 over 1 plus 0, which is 1. That's my slope. So y equals x, or L of x is x, and that's what we were supposed to try to prove. Okay. All right, so that's that for this round. Stop the share, check the chat for more. And let's see, not sure how far we got here. Yeah, so everybody, Prasanna put on the chat a review session if anybody's interested. Thank you, Prasanna, for that. Okay, so let's see. We only have a couple minutes left, so I may not be able to get any of these. 3.69. 3.107. Thank you, Prasanna, for answering that. Okay, we got 4 minutes. Not sure if I can do it, but we'll see. But that might be it after that. Okay, let's see. 3.6, number 9. See if I have time for that. Point 6, number 9. G of x is equal to ln x e to the negative 2. Yeah, we did this one. The key for this one is to not start right away. Use your property of logs. I have ln of a product. That's the sum of the logs, ln x plus ln e to the negative 2x, right? So this is ln of a times b is equal to ln a plus ln b. Okay. And look at this. These cancel out. Ln x minus 2x. That's a lot easier to differentiate, right? So g prime of x is simply 1 over x minus 2, and you're done, which is way faster than going 1 over that, then times the derivative of that, which involves a product rule and a chain rule. So this is a lot faster. So whenever you can use properties of logs, do so. Okay. 3.107, it depends how fast that is. 3.10 number 7. Oh, I already did that, so it looks like I'm caught up. Okay, so 3.10 number 7 is right here. And it looks like it's just about time, so yeah, I'll declare our class to be over. All right, so tomorrow you can ask lots of stuff, and I'll let you have the entire class period, but if that stops, I'll just go on with more stuff, all right? Okay, so that's about it. So have a good afternoon, everyone. We'll see you tomorrow. Okay, bye.